All right, so as mentioned, 1, 7, 1, 8, 1, 9, and 1, 10 are all rational functions. 1, 7 is rational functions and end behavior, and then we'll get into asymptotes and wholes. All that stuff would be in these next couple of sections. So today we're going to talk about domain. We're going to talk about horizontal asymptotes, okay? So what is a rational function? A rational function is a quotient of polynomial functions. So quotient meaning these will be in fraction form. There will be a polynomial on the top and the bottom. So these are like x to the first or x to the second or x to the third in the top and the bottom. You won't see anything with like a square root or negative exponent, nothing weird like that. It says there that q, which is the one in the bottom, cannot be equal to 0, which hopefully makes sense because what happens if the denominator is 0? Makes it undefined, right? So that leads into the domain. The domain of a rational function is the set of all real numbers except the x values that make the denominator 0. So to define our domain, we're literally just going to set our denominator equal to 0. Sometimes we'll be factoring and then solving. Sometimes we'll just solve it. And then those are the values in which the domain cannot be. So they look like this. We're going to find the domain two ways. The first two from our equation and then the bottom from the graph. Notice it says this time to write your answer in interval notation. Okay, so make sure you follow that direction. Yeah. Look at the denominator on A. There's nothing to factor there. If there was, I would. But this is just saying it can't equal 4. And in interval notation, that's negative infinity to 4, union 4 to positive infinity with a parentheses on the floor because it can't equal it. What are you going to do with B first? Factor it. So x plus 6, x minus 6, or you could use even root, but either way, you get that this cannot equal 0 and this cannot equal 0. So x cannot equal negative 6 or positive 6. In interval notation, that would be negative infinity to negative 6, negative 6 to 6, and 6 to positive infinity. Still good?
Why is it the 6 isn't
Because it can't equal the 6. The bracket says it can. All right, then go to C. So C is our graph. Remember that your domain is left to right values. So where these arrows would point in all these directions, it would start with an arrow, which means negative infinity. It comes to this point and it gets close to without touching 0. And then there's a break in my graph. So in interval notation, that would be negative infinity to 0. And then it starts again on this side of my 0, and it goes to positive infinity, which means this is union 0 to positive infinity. We're going to talk more about this tomorrow, but there is a vertical asymptote there, right? That's where it would be undefined, and that's where the break in your domain happens. Questions so far? We remember this, yes? Okay, good. All right, then comes end behavior. So this is where the language changes a little bit. Use limit notation to describe the behavior of the graph as x approaches both infinity and negative infinity. So end behavior does not worry about anything that's happening in the middle here. We only want what's happening on the left end and the right end. So in the little box that's there, notice what's happening, right? This arrow would approach without touching where y equals 0. So the limit notation here would be the limit of the graph as x approaches negative infinity, which means left, as it's pointing left. The actual graph, did I give you an f of x or what? No, so we'll say f of x equals 0. Because it's getting as close to without touching 0. Okay, so 0 is the limit of that side of my graph. Dane?
It's going to be pretty obvious, like where the...
Yeah, and I'm going to teach you how to find your horizontal asymptotes, and that's basically what it is. Yeah. On the right-hand side, That arrow is, again, going towards positive infinity for the x value and getting close to without touching y. If it was like crossing through, if it wanted you to cross, you would see it cross through. It's not like you have to guess that, okay? So the limit of my graph as x approaches positive infinity is what? Good. So both sides are the same this time because they're both approaching the same y at the end. Yep.
Wasn't like the horizontal axis of like the bottom of the equation?
That's vertical.
Oh,
Yeah. We'll do horizontal in a second. It's the relationship between the exponents. Yep. All right, so example 2 says find the end behavior of the rational function using its graph. Again, we're not worried about the middle. We are worried about the left and the right side. So if I look at the left side of this graph, that's read as the limit of the graph as x approaches negative infinity. What's happening to those y values? They're going down. Does it appear as though it will ever stop?
No.
So how do I represent that? Negative infinity. And then on the right side, my arrow is going in this direction. So the limit of my graph as x approaches positive infinity is what? Positive infinity. Increasing without bound. Yep.
So we're not looking at the arrow that's going up because it's in the middle?
Correct. So right now you're only worried about the end behavior.
The arrow going up past the vertical.
You're saying this, right? Yeah. So we'll talk about if that was a vertical asymptote, there is a way to discuss the language as it's approaching the vertical asymptote, but that's tomorrow. All right, example 3, and this is where a calculator comes into play. I'll be honest, this is just like a tedious process. Once you understand the full concept, you won't have to do it every time, unless it says fill out the chart, okay, which is this one, or complete the table. It says find the end behavior of the rational function by completing the table, and then it gives you your g of x. So one way, and I would not recommend this, but one way to do this would for each of these take 4 times 10 minus 1 over 10 squared minus 2 times 10 minus 24 and figure out that value. Then you'd have to do it again, and then you'd have to do it again, and you're doing it 8 times. So can it be done? Yes. Would I recommend that method? No. Okay. The other way is put it in your calculator. So we put it in our y equals, okay? And then I can go to the graph. And then I can go to second trace and I could go to value and I can type in 10. And look at the answer I get. So it's in fraction form, okay? I'm going to show you how to convert that into decimal form, like other than just hitting 39 divided by 6. But in order to do that, I'd have to go back to my home screen, and I don't want to keep going back and forth and back and forth and back and forth and back and forth, okay? So if I was to do this method, which again, I still wouldn't say is the best, but if I was to do this method, I would write a little thing that says 39 over 56. And then I would do second trace, and I would go to value, and I would do 100. And I get an error because it's not in my range, okay? So if it was smaller numbers, it probably would work to continue that way. But when it's not, when it's something like that and it says that, it's just because I'm not zoomed out enough. I'd have to zoom out and then do it again, okay? So my recommendation is instead to go back to our alpha trace and do y equals, and then do a 10. You're still going to get that fraction. Do you know how to convert this to a decimal? How? Besides that. In the math menu, if you go to math, the second thing in the line there says arrow decimal. It's going to convert it to a decimal. So now I know that decimal is 0.696, so on and so forth. Well, it's going to be easier to see the approach with one over the other. Technically, they're both right, but you're going to see in a decimal format because you want to figure out where that limit is happening. Yeah.
How do you convert it to decimal?
I'm here. I'll do it one more time because I'm going to go. Now I'm going to do 100. I'm going to do y1 of 100. It's going to give me the decimal again. I go math. math, and then the second thing in the list, arrow decimal. And that one is 0.408, and so on and so forth. I'm going to keep repeating this process, so then I'm going to do 1,000, 0.004007, so on and so forth, and then do it again, 10,000, and I get 4.007011 e to the negative fourth. What does that mean? It's scientific notation. That means I need to move my decimal 4 places to the left, right? 1, 2, 3, 4. That means it's 0.0004. Now, if I rounded this, what would it round to? If I rounded it to 3 decimal places, what would it round to? 0. What's the problem with that rounded? What do we know about these asymptotes or these breaks in our domain? It actually can't be equal to 0. So you can write 0 point, especially if it says to round to the nearest hundredth, right? I could write that that's 0. But really, I have to know that it's not exactly 0. It's a little bit bigger than 0 because it's not touching 0. Does that make sense? So when I talk about the limit, it can't actually become 0. So it would get as close to without actually becoming 0, and that's what that means. Dane?
So I have 2 questions.
Yeah.
First, is it okay if you write that in scientific notation?
Sure, as long as you know what it is.
Okay.
Yeah.
And also for 100, would you get it wrong if like you did the thing where you plug it into your graph, and because like for 100 it gave
39 over 56. Oh, no, for 100 it said error.
yeah it's an error.
So you have to get a value. There is a value. You'd have to zoom out if you use the graph. Yeah. All right, I'm going to continue to find the other ones. I'm going to do negative 10. And math decimal. This is negative 0.427. And then negative 100. Negative 0.0394, and then negative 1,000, negative 0.003993, and then negative 10,000. And I get negative 3.99 whatever, e to the negative fourth, so move it back. And that is 0.000399 dot dot dot. Okay, again it would round to 0. And the chart really isn't the answer here. The answer is the limit. So we're using the chart to get to it, okay? It is, yes, thank you. It is negative. All of those were negative, okay? So it's important that you establish that even if that rounded to 0, it really isn't true 0 because it can't hit 0. So again, the chart's just helping us get to the real answer, which is to find the end behavior. So if the left side is my positive x values, this is actually going to lead to the limit as x approaches infinity. And the right side is my negative, so this is going to be the limit as x approaches negative infinity. So what happens the bigger I get with my x, the closer it gets to what? To 0, right? Look at these numbers. As you go down this list, they're getting smaller and smaller and smaller and smaller, but never crossing through. So you would get a positive negative if it was actually going to cross through that 0 line. Yeah.
Would it be go for all equations that like if you went by tens after 100 it would have the same first option?
Yeah, because you keep moving and you keep adding a decimal. That's all you're doing. Yeah. Okay.
Why do
Oh,
the values behind the 100 change?
say that again.
Why do the values behind the 100 change?
Because this isn't like a true perfect function. It's not like they're just dividing by 100. Yeah. It's you're dividing by 100 squared minus 2 times 100 minus 24. So the bigger that gets, the least change you're going to see, but it's still a change. All right, how about the limit of x as it's approaching, or as the graph is approaching negative, as the x is approaching negative infinity. So as I come down this line, what's happening to those values? They're getting bigger. They're approaching what? Still 0. So having understood the end behavior here, both of these would have, we would assume there's a horizontal asymptote at 0 because they're both approaching 0 without touching it, okay? But I'm going to teach you like an easy, I think a foolproof way to find your horizontal asymptote, and then we'll talk about how you get the limit after it. So horizontal asymptotes, and this is algebra 2 stuff, so hopefully we remember it, but horizontal asymptotes are horizontal lines, so they are y equals equations. They have to have a y equals. That's one of those things that it's not like if you're listing an answer, if you don't put the y equals here, you will get doctor points. So you need the y equals because it's an equation. It's a horizontal line, okay, that affects the end behavior of your graph. It does not necessarily mean it can't cross through it. So that's where horizontal and vertical asymptotes are weird and different. A vertical asymptote is undefined there. You cannot cross through a vertical asymptote. A horizontal asymptote does not mean it's undefined, so it actually can cross through it. So if you look back into your graph of the last question we just had, it looked like this, even though it had a horizontal asymptote. That horizontal asymptote is affecting the end behavior, not necessarily the middle, okay? So again, a graph can cross through a horizontal asymptote. It cannot a vertical, but it can cross through the vertical asymptote, okay? So when we're talking about horizontal, as it can cross through in the middle there. It doesn't always, like if you look at the one that's there on the actual slide, it doesn't, but it certainly can. All right, so the 3 scenarios for horizontal asymptotes are all based on the highest exponent of your numerator and your denominator. So the highest exponent on my numerator, we call n. The highest exponent on my denominator, we call m. If n is less than m, then it has a horizontal asymptote at y equals 0. If you look back on that last example, the one in the numerator was less than the one in the denominator. It had an asymptote at y equals 0. If they are equal, then has a horizontal asymptote at, and it should be y equals the leading coefficient of the numerator over the leading coefficient of the denominator. So you look for the one with the biggest exponent, you grab the term on the front. And the third scenario is if n is greater than m, there is no horizontal asymptote. Yep. It could be slant if it's one more. And that's in tomorrow's notes. But yes, if the numerator is one more, then the bottom there's a slant asymptote. But there might be neither.
And n is what?
The highest exponent in the numerator. And m is the highest exponent in the denominator. So if I look here, it appears as though there's a horizontal asymptote here, or pretty close to there, okay? Let's say that would be our b value. In this case, it looks like it's like -1, okay? So the end behavior is based on that horizontal asymptote. As we go left here, it's getting as close to that line without touching it. So as you approach -infinity, the limit is at the y coordinate or the y value of your asymptote. And on the right-hand side, it's the same thing. As you approach +infinity, your limit is at that horizontal asymptote. Again, we don't look at the insides yet, the middle. All right, so how do we find the end behavior from an equation? If the rational function has a horizontal if the rational function has a horizontal asymptote, then the end behavior is the y value, okay? Today's a day. So if I had a horizontal asymptote at y equals 1, then the end behavior on both sides is 1. If there's no horizontal asymptote, and this is where it gets a little weird, then the end behavior is either infinity or, this should be an or, -infinity. And to determine that, we do something weird. We take our leading coefficient and we simplify it. So if my leading coefficient in the top was 2x to the third and the leading coefficient in the bottom was x, then we simplify them literally by canceling out an x. And then what's left, we plug in two things. To figure out the left-hand behavior, we plug in negative infinity. And to plug in the right-hand behavior, we plug in positive infinity. So think about what happens here, okay? If I plug in, so let's switch this. This would be the limit as x approaches negative infinity. This would be the limit as x approaches positive infinity. I'm going to take my simplified expression, and for negative infinity, I'm going to plug it in. And for positive infinity, I'm going to plug in positive infinity. So the left is the left, the right is the right. What happens if I square negative infinity? It becomes positive infinity, right? And then 2 times a positive infinity would be infinity. Yes, positive, but positive infinity, right? What happens if I square positive infinity? It stays positive. And if I double infinity, it is still infinity. So the left and the right hand behavior on both of these would be infinity. If you can't grasp the concept of infinity, you could literally plug in a really large number there or a really small number there and see what happens. But if you can grasp that fact, like if I double infinity, it's still infinity. If I cube a negative infinity, it's still negative infinity. So the rules still apply for positive and negatives, okay? But that is going to tell us, and we only have to do that if there's no horizontal asymptote. If there is a horizontal asymptote, then our end behavior is the value of b, or whatever that horizontal asymptote equals. All right, so go to example 4. Find the horizontal asymptotes, then find the end behavior. So if I look at A, what's the highest exponent in the numerator? 1. What's the highest exponent in the denominator? 2. What's the relationship there? Top is smaller than the bottom, which means where's my horizontal asymptote? Y equals 0. The limit on both sides would be 0. So limit x approaches negative infinity, limit x approaches positive infinity would both be 0. It's the if you have a horizontal asymptote, it's the horizontal asymptote. So go to the next one. What's the relationship with the exponents here? They're the same. What happens when we're the same? You take the leading coefficient. So leading coefficient in the top 3, leading coefficient in the bottom 1. So my horizontal asymptote is at y equals 3. Now my limit's at 3. You put the top over the bottom. Yeah. So the limit as I wish I had a shortcut for this every time. And the limit as x. I should just make it a sticker. Oh, why don't I think of things like that? That's how you know you're a real nerd, when you want your Notability stickers to be limit notation. All right, so as it's approaching negative infinity, my f of x equals 3. And as it's approaching positive infinity, my f of x equals 3. Easy stuff, right? Weird, but easy. Okay, now go to C. Highest exponent in the top, 3 in the bottom. What's the relationship? It's bigger this time. It's actually 1 bigger, so there's a slant. We'll get to that tomorrow. There's a slant, but there is no horizontal asymptote. This is where it gets weird. We have to take our highest or our leading terms in both the top and the bottom. So I get 3x to the third over x squared. I simplify these. X squared would cancel, and I just get 3x. Then to find the left-hand behavior, or the limit as x approaches negative infinity, I plug in negative infinity. What happens when I multiply negative infinity by 3?
Negative.
Still negative infinity. F of x would equal negative infinity. The limit as x approaches positive infinity, I plug in positive infinity. And 3 times positive infinity, positive infinity. Yes.
Is there any specific area we have to put the limit in the x approaches?
What do you mean, area? Like as long as it's over. Is that what you mean?
Like I put it over here, but then I also put this there. Does this matter?
This should be, the limit should be over that.
Okay.
So you're saying, because you're saying the limit of x as it approaches infinity.
Okay, so there's.
Or the limit of the graph.
So this should be separate.
Correct.
Okay.
The x of arrow infinity should be under the limit.
Okay.
Questions? All right. Now, if it asks you to find the limit, okay, all you are doing is 1, looking for the horizontal asymptote. If it has it, that is your limit. 2, if it doesn't have it, we're doing what we just did, simplifying our leading coefficient, the leading term in the top and leading term in the bottom, plugging in. But this time, you're only looking for one side of it. So it's going to, instead of you have to do both, it's literally going to say the limit as x approaches infinity. I don't know why I put an 8. Infinity, or the limit as x approaches negative infinity. You only have to do one or the other. That's the only difference. So if you look at this question, it literally will only have one. Okay? It says evaluate the following limit. So the limit as x approaches positive infinity, the only one I'm worried about. If it has a horizontal asymptote, it doesn't even matter. They're going to both be the same. The only time that matters really is when it doesn't have a horizontal asymptote and you have to find it. What's the highest exponent in the numerator?
That's 2.
Good. This would have to be multiplied out to determine that. So it would be 2x squared. What's true about my exponents? They're the same. So this is a leading coefficient scenario. Y would equal 2 over 1 or 2, which means the limit as x approaches infinity is 2. Go to B. What's true this time?
Top's bigger than the bottom.
Top's bigger than the bottom, so
Cancel the 2.
good. There's no horizontal asymptote. We got to grab these two. I'd cross out the x squared and I end up with 3x. And this time I only want to know what's happening as it's approaching negative infinity. 3 times negative infinity would be negative infinity. And C, top's bigger than the bottom. Canceling it, it'd be 3n squared. I only want to know where it's negative infinity, so the left. What happens when I square negative infinity? Goes to positive infinity, and 3 times positive infinity would be positive infinity. That's it, people. Huh? No, because it's already there. It says limit as n approaches. Yeah, it already says it. So that's it. On your homework, which there's a PDF, and then there's the AP classroom is there for today. I actually am holding off on tomorrow's AP classroom when it's just the PDF because we put 2 sections together. There is one question that talks about a slant asymptote. Feel free to skip it for today. If you remember the slant asymptote, feel free to use it, okay? But also I think it's number 4. Don't freak out, okay? If it's there and you don't understand it, we're going to eventually go back to it.